expecting, okay?
1.
All right, we're going to show something interesting here, which is a little bit sophisticated, and that is that every regular language is in Nick's class. So I'll write that as the class of regular languages is a subclass of Nick's class. So the best way to show that is with an example. Let's say we have a language L, and we want to know whether this string is a member of L, B, A, B, B, A, 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 B, where L is the language accepted by this particular DFA. DFA has a start state 0, and the alphabet is A, B, and the final state is 2. And this is the alphabet. So what we can do is we can do basically a layered graph. And here's the layered graph up here, where the column is one layer, and it consists of a copy of each of the states of the DFA-N. Now, we then copy the strings of W above them, so each transition from one layer to another is labeled by one of the members of the alphabet. And then we draw arrows between the layers. Now, I didn't put arrowheads on the blue lines because, well, just think every arrow, every one of these lines is an arrow going from left to right. All right, now here, if you notice that if there's a B, 0 goes to 0, and 1 goes to 2, and 2 goes to 1. So I draw arrows this way from 1 to 2 and from 2 to 1. Now if there's an A, I draw an arrow from 0 to 1, and an arrow from 1 to 2, and an arrow from 2 to 2, and so forth. Now, it would take only O of n time with one processor to go dynamically through this and determine whether this particular string is accepted. And that acceptance means that you would end up in the last layer at the final state, which is 2. And here we exit to show that it's accepted. Now, what we're going to do instead is basically use what turns out to be a form of matrix multiplication to condense the problem. So every 3 layers, consecutive 3 layers, can be condensed into 2 consecutive layers by combining the arrows. All right, now I'm going to walk through this. The number of layers is halved every time. Well, not exactly. This was 9 layers, this is 5 layers, 3 layers, 2 layers. And eventually, from this one, we'll be able to see the answer. So what we do is we combine this. If we take a combination here of BA, then 0 goes to 0, then to 1. Here, 1 goes to 2, then to 2. And 2 goes to 0, I'm sorry, to 1, which then goes to 0. So we have arrows here. I can draw the arrowheads now because it's there's a little more space. But this is now the arrows of the transitions from layer 1 to layer 3. Or if I prefer, I guess I should call it layer 0 and layer 2. Because layer 0 refers to before I have read one symbol. So I have read 0 symbols. And this layer corresponds to what the situation is after I've read the first 2 symbols. All right, now I use these rules here to define what happens in this case. So what happens in this case, when I combine these 2 diagrams, I get arrows going straight across. Now likewise, when I combine these 2 diagrams, I got arrows going straight across. And when I combine these 2, I get 0 to 2, 1 to 0, and 2 to 1. All right. Now, we continue this process, combining these arrows together to get arrows between layer 0 and layer 4. So we have this, combining this, 1 to 2 here, and 2 to 0 this way. All right, finally here, let's keep going. 0 goes to 2, when I combine these two. 1 goes to 0, and 2 goes to 1. Now, in the last analysis, what we're going to do is 0 goes to 1 and to 0, 1 goes to 1, goes straight across, and 2 goes to 2, which is straight across. Now we observe that if we start at 0 in layer 0, we get to 0 in layer 8. And therefore, that's not the final state, so we can conclude that this particular string, BABBAAAB, is not a member of L. We could, on the other hand, if we had an arrow this way, we would conclude that it is a member of L. All right, now what's the point of this? There are log n layers here. It only takes log n layers to get down to where we have a simple thing going across. Now, that means that we can do it in log n time if we can do each layer if we can get a transition from this layer to this layer in constant time, and we can if we have enough processors. We put one processor to work here to create this graph, another processor here to create this graph, and so forth, and then finally a processor here and a processor here. So a total of 8 processors working in approximately 1, 2, 3 steps, which is roughly log 8, will give us the answer. And thus, this regular language is an NC. Now, doing this for any regular language, the technique should be clear. If you have a DFA-M, then you draw a picture like this, a layered graph, where there's one layer for each, one layer, 0, and then 1, 2, 3, up to n, where n is the length of the string, and you label the transitions between the layers by the symbols in the string. Then, using only one processor in constant time, reading the graph, you can draw the transitions from 0 to 1, 1 to 2, and so forth. And those are all done simultaneously. Then you take those results and combine them, and the rules for combining them would be the same at each time. And that way, any regular language is a mixed class.
Fine.
Now let's talk about some more problems which are in the mixed class. If I have the sum of n numbers, we can do this in logarithmic time. You simply add the first two, then the third and fourth, the fifth, sixth, seventh, and eighth, and get subtotals. Then add the first and second here, third and fourth there, and then finally add those two. And of course, the n is 8 in this case. You take 3 steps, which is log 8. Or we could find the maximum n numbers. Here you take the maximum of each pair, first and second, third and fourth, and so forth, and do the same thing. So the paradigm is exactly the same. So finding the max of a bunch of numbers or finding the sum of a bunch of numbers is in mixed class. Okay.
1.
Here's a small list of a few other problems in mixed class. Sorting an array, well, we're thinking that as an algorithm. An NC algorithm means there's an algorithm that can be carried out with polynomially many processors in polylogarithmic time. So given an array as the input, you want the sorted array as the output, where n is the length of the array. And so you wanted logarithmic, polylogarithmic of n time. Now, addition of integers, you're only talking about 2 integers here. But when we talk about the size, we're talking about the number of bits. So if we have 2 n-bit integers, let's say each one consists of n binary bits, then the question is how fast does it take to add them? Now, the standard method in elementary school is what's called a ripple adder, where you start from the right and ripple the carries to the left. Well, that takes linear time in the number of bits, which of course takes very little time in a computer, but the amount of time it takes is significant if you do a lot of additions. So computers nowadays use a carry look-ahead adder, which will work in polylog time as a function of the length of the integer. Now, multiplication of integers is also a mixed class problem, and you can do matrix operations, determinant, matrix multiplications, and various other things. And here's another one, maximal matching, which is a graph theory problem.